All right, so this is Math Stat 341 probability. This is lecture 21. I am flying to Charlotte tomorrow, but that is not why I'm wearing this hat. This is the high point of the semester, right? In this class, we have the central limit theorem. Central is basically similar to fundamental. You've seen a couple of fundamental theorems in other classes. Fundamental theorem of algebra, fundamental theorem of arithmetic, fundamental theorem of calculus. Sometimes people talk about the fundamental theorem of linear algebra, so it doesn't feel left out. It's rare to have a fundamental theorem. Solution key is here. So whenever you have something like that, it's extremely important. And so what I want to do today is I want to give as much of a proof of the central limit theorem as I can. Later in the semester, if there's some interest, I might talk a little bit about some of the complex analysis that's needed to make the proof fully rigorous. We've already seen, looking at things in real analysis, how difficult the subject can be. We have a situation where we have a function, all of whose derivatives at 0 are 0, but the function is not identically 0. So knowing the Taylor series is not sufficient to knowing the function. Similarly, knowing the integral moments is not sufficient to determine the distribution. So big question is, when is that enough? When does that determine what do I need to know? How many moments do I need? Which moments do I need? And so to do this rigorously requires complex analysis. That is a class that should be offered next year. And if you're interested in stuff like this, great thing to do. And again, we're towards the end of the semester now. This is the time to start talking about what might you do next and why might you want to do that. All right, we will talk a lot about doing simpler cases first and building intuition. We've already done that by looking at flipping a fair coin. And we saw just how bad the calculation was just in that case. And I encouraged you to try to do a biased coin and see if you could prove the central limit theorem directly in that case using Stirling. Or even in the biased case, is it already so bad that you might as well just do the general case? We did talk a little bit about applications of the central limit theorem by looking at Poisson random variables, but it's very rare that you have a nice closed form expression for the sum of independent, identically distributed random variables. The central limit theorem basically says, for the most part, it's going to be really well approximated by a normal distribution. And then we will adjust the mean and the variance so that it's mean 0, variance 1. As always, whenever you see a product, you should have a Pavlovian response, take logarithms. And the reason is we are just more experienced with adding than multiplying. There's no difference. When I was a postdoc at Ohio State, I had a $10 gift card to Walden Books. I figured I might as well use it. And I was curious where Walden Books was. The internet was not as big back then. So I actually physically picked up a phone and called the store and asked, where are you located? I'll be coming from the Ohio Stadium because everybody in Columbus should know where the Buckeyes play. So I asked, how many miles are you from Ohio Stadium? Oh, I'm sorry, I'm from Canada. I don't think in miles. So I said, okay, how many kilometers are you? I can do the conversion. Oh, I don't know. But she doesn't know the distance in kilometers. It's not that she doesn't know the distance. She just doesn't know the distance in kilometers. Does it matter if we measure things in miles or kilometers? No, we can do the conversion back and forth. Does it matter if we look at products or sums? No, but we all have this natural tendency. We understand sums better. We just have more experience with them. So it's not a bad idea to just take the time and convert things to sums. Okay, so we've talked before about the moment generating function. So if x is a random variable with density f, then the moment generating function is defined as follows. It's basically the expected value of e to the tx. And so it's not clear that the moment generating function will always converge. If I give you, for instance, a Cauchy distribution, its moment generating function will not converge for any t other than t equals 0. For other distributions, it might converge for positive t, but not for negative t, or vice versa. It turns out, and this is where we need complex analysis, if the moment generating function converges in a small neighborhood about the origin, then life is great. But we need a small neighborhood in both directions. And by going in both directions, then that means, when x is positive, we have an exponentially increasing factor. When we go in the negative direction, when x is negative, negative t times negative x becomes positive. We have an exponentially increasing factor. So the probability distribution has to have at least some level of exponential decay for things to exist. If the distribution has finite support, then these integrals will always converge, these sums will always converge. Okay, so again, the moment generating function is just the expected value of e to the tx, so the hope is we can do these integrals or these sums. So we talked about a bunch of properties of the moment generating function. So this is all the view, but it's not bad to just quickly refresh ourselves before we go into a long set of calculations. So not surprisingly, when you look at the Taylor series expansion of the moment generating function, you get the coefficients are the moments divided by the factorials. Hence the name moment generating function, right? When you trick the series expansion, you get the moments. The next thing is if I do a simple change of variable, the moment generating function changes very simply. The moment generating function of the new variable alpha x plus beta is just e to the beta t, the moment generating function of x at alpha t. So it's a very simple translation. And the proof of that is not too bad. If y is equal to alpha x plus beta, then the moment generating function of y is the expected value of e to the ty, and then that's just the expected value of e to the alpha x, t times alpha x plus beta. And now we basically just multiply things out, pull things outside of the expectation because it's a constant. Okay, the next one is one of the reasons why the moment generating function is so useful to look at. I didn't realize there was something there. All right. So if x1 and x2 are independent random variables with moment generating functions mx1 and mx2, then the moment generating function of the sum is the product of the moment generating functions. And we saw earlier in the semester just how nasty it is to write down the explicit closed form expression for the sum of 4 uniform distributions. And if it's bad for just 4 uniform distributions, imagine 30 uniform distributions with the nightmare of cases. This is wonderful. The moment generation function of a sum is the product of the moment generating functions. And if x1 equals x2, then it's just squaring it, or more generally, if all the same. So if all same, the moment generating function of x1 plus xn of t is just the moment generating function of x1 of t to the nth power. And then the hope is that maybe the nth power of the moment generating function is going to converge nicely to a normal distribution. And we'll use the second property to just adjust things so that it has mean 0, variance 1. Okay. And so that's, the next slide, the standardization of a normal, the standardization so we can compare it to the normal. This is very similar to, if you remember your log laws, the most forgotten log law is the change of base. If you know logarithms in one base, you know logarithms in all bases. Without loss of generality, why don't we just adjust things and translate so it has mean 0? Why don't we just adjust things so it has standard deviation 1? Just change the units we're looking at. Going from like Celsius to Fahrenheit. Changing the base point, changing the scale. And so what we do is we take a random variable x, we subtract its mean, and then we divide by the standard deviation, and that new quantity will have mean 0, variance 1. And so typically what we'll do is we will look at a sum of independent identically distributed random variables, subtract the mean of the sum, divide by the standard deviation of the sum, and that new quantity will have mean 0, variance 1. And hopefully that will converge to the standard normal. If we didn't subtract the mean and we didn't divide by the standard deviation, it would just be converging to a different Gaussian. It might be converging to a Gaussian with growing mean and growing variance. This way, we only have to look at knowing one normal distribution. So the next is Theorem 20.5.1, the moment generating function of a normal distribution. So if I give you a normal distribution with mean mu and variance sigma squared, then the moment generating function of x is e to the mu t plus sigma squared t squared over 2. So in particular, if it has mean 0, variance 1, it's just e to the t squared over 2. I really only need to do the case of the standard normal because we have result 2 here, which says if I know the distribution of x, I know the distribution of alpha x plus beta. So if I just multiply by alpha, I can adjust the standard deviation from 1 to being sigma by just taking alpha to be sigma. If I then want to shift with the mean, I can just choose beta appropriately. So I really only need to calculate the moment generating function of the standard normal. And so that would be the expected value of e to the tz. Okay. So we'll need to do that calculation. Okay. Any questions so far? So this is just setting the stage for my making an algebra mistake today. Right? So please watch carefully. Almost surely there will be at least one algebra mistake, hopefully only one. All right. So here are the black box results we are going to assume from complex analysis. So the first is assume the moment generating functions for x and y exist in a neighborhood of 0. So I can go a little bit to the left and a little bit to the right of 0. And assume the moment generating functions are equal in that neighborhood. Then their cumulative distribution functions are the same. And since the density is the derivative of the cumulative distribution functions, then the densities are the same. This seems reasonable. You shouldn't be able to have two moment generating functions that are equal for infinitely many values over an entire continuous range unless they're coming from the same distribution. But remember, we do know things such that that strange function e to the negative 1 over x squared, where all of the Taylor coefficients are 0, but it's not identically 0. So I could add that to any function and not change its Taylor series at the origin. So we have to be careful. So it turns out knowing the integer moments is not enough to uniquely determine the probability distribution. This gives us not just the integer moments, but a little bit more. Right. The next one is imagine we have a sequence xi of random variables with moment generating functions m of xi. Assume there's a delta such that as long as t is less than delta, in that little interval about the origin, from minus delta to delta, the moment generating functions are converging pointwise to the moment generating function of some nice random variable, say mx of t. Okay. Then there exists a unique cumulative distribution function f whose moments are determined by the moment generating function mx, and at all x where fx is continuous, then the cumulative distribution functions of the xi's are converging to the cumulative distribution function of x. So again, in words, we have a small interval about 0 where things are converging. They're converging to some nice function. It turns out that the function they're converging to has some associated cumulative distribution function attached to it. And the only way they can be converging is if the corresponding cumulative distribution functions are also converging. So the moment generating functions converging to something nice means the cumulative distribution functions converge to something nice. Okay. We have to be a little bit careful because we may not always be in a situation where things are continuous. So there's a lot of technical conditions. This is a first course on the subject. I have no problem assuming some results from complex analysis that seem reasonable. They're basically saying, if one thing converges, a related thing converges. And then you go to an advanced math class to just see, well, what conditions do I need to ensure that convergence of one implies convergence of the other? But it seems reasonable that if I put on sufficiently restrictive assumptions about my functions, I should be able to have some kind of claim like that. Exactly what those conditions are, I don't know. Well, actually, I do know. They're right here. Right? Why are those enough? There could be other ones that work that are even weaker. And sometimes there's a whole industry. I don't know if you've ever heard or seen the TV show Name That Tune, where people compete as to how many notes do I need to hear before I can name that song. And people often do this with math theorems. I can prove this math theorem holds with these conditions. Or yeah, I can do it with one less condition than you. And what's the fewest number of conditions you need to have something? What's nice about this is then your result is more applicable. The fewer conditions you have, the more things you can apply it to. However, the harder it's going to be to prove because the less you have to work with. And so these are a good set of conditions that are frequently met in practice. And so the functions we're looking at, it's not going to be hard to verify that these are true. It's very similar to if you want to make me feel good about your education, nod your head and say you've seen a proof of the fundamental theorem of calculus. And if you've seen a proof, they probably assume not only is the function continuous, but maybe the function is differentiable and the derivative is bounded, some nice condition like that to show that the upper and the lower sums converge to a common value. You don't need that. You can do it with real analysis with uniform continuity, but that requires more work. Or you can bypass that by assuming that your function has additional properties. You don't need those additional properties. It just makes the work harder. Okay. So now, moment generating function versus characteristic function. So the moment generating function of x is defined as the expected value of e to the tx, which is the integral, let's say, from minus infinity to infinity of e to the tx f of x dx. Can somebody give me a distribution where this does not exist in a neighborhood about the origin? So where it doesn't exist, for all t close to 0, if f is what? Or we'll say fx is what? So can you give me a distribution where the moment generating function is not going to exist for all t in the neighborhood of the origin? So what's your go-to example of a distribution that's bad? Cauchy, right? When in doubt, go with Cauchy. That would be the integral from minus infinity to infinity of e to the tx 1 over pi 1 plus x squared dx. When t is negative, you have exponential decay, which is great, but when t is positive, you have trouble. So trouble if t is greater than 0. Also issues if x is exponential with some parameter lambda. Because if x is exponential with some parameter lambda, then you'll be okay if t is negative. Or will we be okay? We might be okay. So if we do that, we would have the expected value of e to the tx. So that would be the integral from 0 to infinity, right? So we would have e to the tx 1 over lambda, e to the negative x over lambda dx. Is this going to make sense? Will this make sense for t on both sides of 0? What do you think? If t is negative, is the integral going to be okay? Will the integral converge if t is negative? Yeah, all the exponentials will have negative. So everything is going to be fine if t is negative. What if t is positive? If t is sufficiently small, are we okay? Yeah. So you're okay if t is less than 0. If t is greater than 0, we have 1 over lambda, integral from 0 to infinity, e to the negative 1 over lambda minus t x dx. And we're okay if t is less than 1 over lambda. So this moment generating function will exist on both sides of 0. So the Cauchy was bad. The exponential, even though we could have some issues, now let's see, we're going to be okay. Because it's only defined for x greater than 0, when t is negative, everything is fine. We get some extra decay from that. Extra decay can't be bad. You know, if you were a finite integral before and I now make you smaller, you're still going to be finite. What about if we take a positive value of t? Well, if t is really, really small, t is going to be less than 1 over lambda. And if t is less than 1 over lambda, it's still going to integrate to something finite. So I'll leave it to you to figure out what that integral is. Yeah. You just have to do a change of variable. It's not too bad to do that integral. Unfortunately, the fact that the Cauchy distribution exists means you can have probability distributions whose moment generating functions don't exist in a neighborhood. So we sometimes look at the characteristic function. And it's extremely similar. So phi x of t is the moment generating function at it, or it's the expected value of e to the itx. So it's the integral from minus infinity to infinity of e to the itx f of x dx. And so the point to note is the absolute value of e to the itx is the absolute value of cosine tx plus I sine tx equals 1. So integral exists. So this is the advantage of the characteristic function over the moment generating function. The characteristic function always exists. It is much easier to work with objects that exist than objects that do not exist. Does anybody know another name essentially for the characteristic function? You might have seen it in another class. Instead of e to the itx, they often have e to the negative 2 pi itx. Has anybody seen this? It's related to the Fourier transform. And there's a lot of different normalizations of the Fourier transform. Do you have 2 pi or not? Do you have a minus sign or not? But it's basically the Fourier transform. Right. So if you work with characteristic functions, then you're always working with something that exists, and that makes some of the arguments a little bit easier. All right. So just to review, you should have seen this so many times that you can rattle this off in your sleep. If I give you a normal distribution with mean, mu, and variance sigma squared, then its density is 1 over square root of 2 pi sigma squared, e to the negative x minus mu squared over 2 sigma squared. And in the central limit theorem, and that's what we're going to try to prove today, is let's assume we have n independent, identically distributed random variables whose moment generating functions converge in some neighborhood of 0. So I can go from minus delta to delta, and everything exists. I'll denote by mu and sigma squared the mean and the variance of the x's. We're going to look at the sample mean, x and bar. So we're going to add up the x's and divide by n. Well, we know that the expected value of x and bar is just going to be the sum of the expected values of the xk divided by n. And since they're all the same, it's just going to be n times mu over n, which is just mu. And similarly, if I want to calculate the variance of xn bar, that's going to be the sum of the variance of the xk. And now we divide by n squared. Because remember, if you multiply a number by 5, the variance changes by 5 squared. And then that way the standard deviation only changes by a factor of 5. So we have n copies in the numerator. So we'll get n sigma squared over n. So we get the variance is sigma squared over n. And that's why we divide by sigma divided by the square root of n. So now Zn is going to have mean 0 and variance 1. So it's at least reasonable that Zn is going to converge to a standard normal. It's at least now adjusted so it has mean 0. It's at least adjusted so that it has variance 1. Whenever you see a mathematical miracle, you want to pause and ask why. Why do we have such a fundamental result? Why do we have the fundamental theorem of calculus? What is going on that allows us to find areas from antiderivatives? Why does it not really matter what distribution the x's are? Why should it always be converging to the normal? Well, what's really going on is if I give you any nice distribution, I can adjust it so it has mean 0. That's just a simple translation. I can rescale so it has standard deviation 1. So any distribution with finite mean and finite variance, without loss of generality, it has mean 0 and variance 1. It's not until you get to the third moment or if the distribution is symmetric about 0, the fourth moment, that you actually see any shape of the distribution. The first two moments are independent of the shape of the distribution. And it turns out when we calculate what's going on to prove the central limit theorem, only the first two moments matter in the limit. And that's where the universality comes from. Because if only the first two moments matter, and I can always adjust so that everything has the same first two moments, then I'm going to get the same answer. The other moments should matter somewhat, right? Adding a bunch of exponentials is not the same as adding a bunch of uniform. The way they matter is the rate of convergence to the normal. The third and the higher moments, the shape of the distribution, they impact how quickly does it settle down. And this is where a lot of people say, if it's 30 data points, that's enough so that you can use the central limit theorem without getting in trouble in a class. But you really want to get a sense of how many points do you need to be confident that you're within a certain tolerance? Yes.
So I'm just like thinking about the intuitions around this, and the first thing that stands out to me is it's odd that it would be the first two moments as opposed to like just the first one moment. Like I understand, that in the limit,
right,
you're going to see the smaller things dropping away.
Right.
But yeah.
So we'll see that when we start doing the algebra in terms of we're going to be taking the log of a product, and in terms of which terms can survive when we do a Taylor expansion, we're going to have a really large factor outside the logarithm. Once we get to a third term and higher, they're not going to really be contributing. And so in terms of at a higher level, why do we need the first two? I mean, the best I could say is we can always just adjust things so that the first two are whatever we want. And
we can't do that for the third.
Not by a simple linear rescale. So remember, the only type of rescaling we're allowing ourselves to do is alpha x plus beta. And if we do something like that, we can always adjust the first two moments. But we can't do anything with the third. The third moment is the first moment that's going to fundamentally tell us about the shape of the distribution. But the variance, we saw this with Chebyshev's theorem, the standard deviation, that tells us the scale at which to look at things.
So is there a more... Is like the central limit theorem almost a special case where not a special case, but like it comes out of the fact that the way we're defining the normal distribution is in terms of these sort of like we're saying it's independent to these two things, the first two moments.
Well, the normal distribution is a specific distribution.
Yeah.
So let's do the calculation, and then after we do the calculation, see if that answers your question. If not, then let's ask it again.
Great.
But again, at this point, it doesn't seem entirely unreasonable that we could have a universality in play. It's not a proof. It's just from what we've seen, I can always adjust to have mean zero variance 1. So maybe there's a hope. And then the question is, why should it be the central limit theorem that pops out that we have no idea about yet? Okay, so let's compute the moment generating function of Zn. So before we do that, let's calculate the moment generating function of the standard normal. Right? So let's let Z be normal with mean zero variance 1. And the moment generating function of Z is going to be the expected value of e to the tz right? So the moment generating function of Z is going to be the integral from -infinity to infinity, e to the tz, 1 over square root of 2 pi, e to the negative z squared over 2 dz. Okay. Any thoughts about how we should handle the algebra? We have an e to the tz, we have an e to the negative z squared over 2. What could we do? So we could pull out things that don't depend on z. We can pull out the 1 over square root of 2 pi. How should we handle the e to the tz and e to the negative z squared over 2? Yeah, put them together. So let's look at the exponent. So the exponent is going to be negative z squared over 2 plus tz. So I'm going to pull out a minus a half, and I'll have a z squared minus 2t z. Is that correct? Okay. I clearly want to do something based on where I put the parenthesis. Right? What would I like to do? As Seinfeld would say, I'd like to do, yeah, I'd like to do nothing. And I'm going to do nothing by adding. So what should I add? I should add 0. And how should I add 0? Plus t squared and then minus t squared. So this becomes minus 1/2, and then z squared minus 2tz plus t squared is z minus t squared, right? And then we're going to have a plus t squared over 2. So we get mz of t is the integral from minus infinity to infinity, 1 over square root of 2 pi e to the negative 1/2 z minus t squared plus t squared over 2 dz. I can pull the t squared over 2 outside the integral, bless you. I integrate from minus infinity to infinity, 1 over square root of 2 pi e to the minus 1/2. I'll do it this way. Bless you. Bless you. E to the z minus t squared over 2 dz. What's that integral equal to? You know what that integral is. Normal. What normal is this? This is a normal. Normal t standard deviation is what? So the integral is what? It's a probability distribution. It's just 1, right? So we get that the moment generating function, as claimed of the standard normal, is just e to the t squared over 2. Okay? So far, so good. And again, we got to do nothing, right? Now, what we could do is we could look at a lot of specific examples. We could take a Poisson, and we could calculate sums of Poisson, which is a Poisson, and then see if the moment generating function converges to this. We could take sums of chi-squared, which is a chi-squared, and see if it converges to this. I could do sums of normals, but I know the sum of normal is normal, so the central limit theorem is actually not that hard to show in that case. But to build intuition, we could actually roll up our sleeves and do the algebra. And this is something where, as a professor, I struggle. I could easily do another class where we go through the algebra and then say, let's do a search and replace and see that really we never used too much of the properties. It simplified the algebra a little bit, but we could do the general case. If people would like, I'm happy to do Poisson and then do the general case, or we can just do the general case. First loud voice often wins. Do people want to just do the general case, or do people want to do a specific case first? I'm sorry? All right, let's do specific case. First loud voice wins. So what I will do is I will jump down here, and then I'll eventually just move the slides up. Okay? So let's, so which one do we want to do? Have we calculated the moment generating function of the Poisson? Or actually, we just did the exponential a few moments ago, right? So for the exponential, if x is exponential with parameter 1, then the moment generating function of x was just the expected value e to the tx, And that's the integral from 0 to infinity of e to the tx 1 over lambda e to the negative x over lambda dx. Okay, so we saw that that was 1 over lambda integral from 0 to infinity e to the negative 1 over lambda minus t x dx, right? So we need to calculate what this integral is. So let's change variables. Let's let u equal 1 over lambda minus t times x. So du is 1 over lambda minus t dx. If x goes from 0 to infinity, where does u go from? It's also going to go from 0 to infinity. Right? Okay, so if we're going to do that, I have a dx. I don't want dx. I want 1 minus lambda minus t dx. Not a big deal. I divide by 1 over lambda minus t, and I multiply by it. So then I have 1 over lambda minus t dx. Now I change variables. I'm going to multiply the lambda and the 1 over lambda minus t, and that's going to get me a 1 over, I think, 1 minus lambda t. And then we'll have the integral u goes from 0 to infinity, e to the minus u du. All right. What's the integral of e to the minus u from 0 to infinity? You could do the integral directly, but this is the probability density of which exponential? It's an exponential with parameter 1. The integral just has to be 1 because it's a density. If you don't remember that, 1 minus lambda t inverse, it would just be negative e to the minus u at 0 and infinity. When I plug in infinity, I get 0. When I plug in 0, I get negative 1. So we just get 1 minus lambda t inverse. So that would be the moment generating function of the exponential. Okay. Does that look familiar to you? This is 1 over 1 minus lambda t. Does that look like anything you've seen before? Where have we seen something like 1 over 1 minus something? Yeah, it looks like a geometric series. So this is just going to be 1 plus lambda t plus lambda squared t squared plus dot, 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 dot. But we also know that the moment generating function is 1 plus mu1t plus mu2. So I'm just going back to over here with the primes. The first moment, the second moment, the third moment just divided by the factorials. That was one of the things we proved by just taking the exponential, replacing it with the series and integrating. And we just switched the integral of this, the integral and the sum. So when you look at the expansion of the moment generating function, you just get the moments, not the centered moments, the moments. So I did guess correct. Okay, so I didn't write a prime here because the first moment is really the same as the mean, but I'll put a prime here. The second moment prime, so the second moment over 2 factorial t squared plus dot, dot, dot. So looking at this, what's the mean? The mean mu is lambda. The second moment, mu2 prime equals what? So I'm sorry, equals 2 lambda squared. So the variance of x is the expected value of x squared minus the square of the expected value. All right, so we have 2 lambda squared minus lambda squared. That's just lambda squared. And so the standard deviation of x is just lambda. So because we know the moment generating function, we can just quickly pull off the mean and the standard deviation. They're both lambda. That's nice. Okay, so we know the moment generating function of x. Now what we want to do is we want to look at Zn is going to be x1 plus xn over n, the sample mean, subtract off the mean of each one, and what is the mean of each one? What did we just show the mean of each one is? Lambda. So we subtract off lambda, and then we divide by sigma divided by the square root of n. What's sigma? No. Sigma squared is lambda squared. The variance is lambda squared. It's just lambda. So the mean and the standard deviation are both lambda. And so we would divide by lambda divided by square root of n. You could also look at x1 plus xn, subtract off n times the mean. And now what would be the variance? The variance now would be n times the variance before. So the variance would be n sigma squared. So the standard deviation would be square root of n times sigma. So it would be lambda square root of n. So the question is, are these two really the same? Well, we've got a lambda down below and a square root of n. So that's the same as moving the square root of n upstairs. So this becomes x1 plus xn divided by lambda square root of n. Multiplied by square root of n over lambda, square root of n over lambda. This is going back to old algebra and making sure we don't make a mistake. That can't, this is the joy of a divided by b divided by c, right? We want to do this so we don't make an algebra mistake. So if I multiply by square root of n over lambda, I clean up the denominator to be just 1. The square root of n makes the n square root of n, and we'll have a square root of n lambda. And then we have lambda times the square root of n over lambda. That's just going to be minus the square root of n. And notice what we got here is x1 plus xn. Oh, did I make a mistake? No, okay, no, that's fine. And then if I want to keep this over the lambda here, I have to make sure I don't divide by the lambda. So minus lambda square root of n if I want to have a common denominator. And that's exactly what I have over here. So if I want to keep, did I make a mistake? This is an n over here. Oh, wait, no. I told you I'd make an algebra mistake if I tried to do this. No, it is the square root of n. Okay. And then the other one is going to be yes, minus lambda over n. Okay, so minus And I want to keep everything with the lambda square root of n. So there's no lambda here. Okay. And then, okay. If I put the lambda there, then, okay. So if I put the lambda there, then there's the lambda here. Okay, this is the danger of always doing the algebra. Okay. And now, the only issue is, do I have the right n up here? All right, so have I made a mistake on the right-hand side? I look at the sum of the x's, I subtract n times the mean, and then the variance is going to be n lambda squared, so it's square root of n lambda. Okay. And then over here on the other one, I have the sample mean. The mean is going to be 1 over n squared, lambda squared, and so it's lambda squared over n divided by lambda squared of n. Good, square root of n cancels. Okay, okay, good, good. Yeah. Okay, good. That's fine. Yes. This should be a square. This should be right. So if I'm looking at what's going on over here, I have lambda times square root of n. And so that's the lambdas cancel. And this term over here is just going to give me a square root of n. But I then want to have it over denominator lambda square root of n. So if I want to have it over denominator lambda square root of n, I have to multiply by a lambda square root of n. And now I get a lambda n over lambda square root of n. Okay, so now everything matches and the two expressions are the same. So I can either calculate it by looking at the sample mean, subtract off lambda and divide by the standard deviation of the sample mean, or I could just look at the sum of the x's, subtract off its mean and divide by that standard deviation. Both of them are going to give me the same quantity. Either way I look at it, I'm left with, I need to understand this sum. So we have to study x1 plus xn over lambda square root of n minus, the lambdas cancel and it would just be minus square root of n. So there's lots of ways of looking at it. And I'm trying to write something of the form alpha x plus beta, because the moment generating function of alpha x plus beta is just going to be e to the beta t, the moment generating function of x at alpha t. So that was one of our results from before. So if I have the moment generating function of alpha x plus beta, it's e to the beta t moment generating function of x evaluated at alpha t. So going to what we have over here, we have to figure out what is alpha, what is beta. Well, here, this x1 through xn, that's going to be my x. Alpha is going to be what? So what's the coefficient of x? So what would you, I'm sorry? 1 over lambda square root of n, right? That's the coefficient of the x. What's beta? That's just going to be negative square root of n. So when we plug that in, just move it over so we have a little bit more space. So when we plug that in, we get e to the beta t. So it's going to be minus square root of nt. And then the moment generating function of x at alpha t. So it's going to be t over lambda square root of n. Okay. So let's keep going. So we have the moment generating function of Zn of t was e to the negative square, was it negative or positive? Negative square root of nt. And then the moment generating function of x1 plus xn at t over lambda square root of n. But all the x's have the same moment generating function because they're all exponentials with parameter 1, right? So this is just going to be e to the negative root nt, the moment generating function of one of them at t lambda root n to the nth power. Is everybody comfortable with that? We're using the moment generating function of a sum is the product of the moment generating functions. So going back, that's the property over here. The moment generating function of a sum is the product of the moment generating functions. Since they all have the same moment generating function, it's just the first one to the nth power. Okay. Okay. Somewhere over here. All right, there we go. All right, so now what is the moment generating function of an exponential with parameter lambda? Well, fortunately, we just calculated that. Right? Its moment generating function was 1 minus lambda t, inverse. But the moment generating function of x1 of t is just equal to 1 minus lambda t inverse. Given how easy it is to make an algebra mistake, I'm going to go through it slowly. And let's just take the moment generating function, and we're going to evaluate it at t over lambda root n. So it's 1 minus lambda, and now t is just t over lambda root n inverse. So this is just 1 minus t over square root of n inverse. Okay. What is the easiest place to evaluate a moment generating function? What value of t is the easiest? 0, right? You're taking the expected value of 0. What's the expected value of 0? Well, I'm sorry, it's the exponential of 0. Sorry, the expected value of the exponential of 0 is just going to be 1. So the moment generating function at 0 is always going to be 1. So if you think about it, what are we doing? We're evaluating the moment generating function at t over essentially square root of n. We're evaluating the moment generating function really close to 0. So it should be really close to 1. However, we're raising it to the nth power. So if you have something that's a little bit less than 1 and you raise it to a huge power, it could now become a lot less than 1. That's where things get interesting. So the moment generating function of Zn of t is e to the negative root nt, 1 minus t over root n to the negative n. What should we do now? How should we figure out what happens as n goes to infinity? You should have a Pavlovian response at this point. It's deep enough in the semester. What should you do? Take a logarithm, right? So if we take a logarithm, so we would get the log of the moment generating function of Zn of t. Okay, when we take the log of a product is the sum of the logs. I'll do it slowly. We'll get the log of e to the negative root nt plus the log of 1 minus t over root n to the minus n. All right, so the first term is just going to be minus root nt, because the log of e to a power is just the power. Then we'll get minus n, the log of 1 minus t over square root of n. But we all remember the log of 1 minus u is minus u squared over 2 minus u cubed over 3 minus dot, dot, dot. This is just one of the expansions you need to know. The log of 1 plus u is plus u minus u squared over 2 plus u cubed over 3 minus dot, dot, dot. And of course, if you just replace u with minus u, you can go from either one to the other. It makes sense. If u is a small positive number, 1 minus u is it's a little bit less than 1, so its logarithm should be negative. If u is a small positive number, 1 plus u is a little bit greater than 1, its logarithm should be positive. So these expansions make sense. The log of 1 minus u should start off with a minus u. The log of 1 plus u should start off with a plus u. So now we get the log of the moment generating function of Zn is just going to be minus square root of nt minus n. And now let's expand out the log of 1 minus t over root n. So u is just t over root n. So the first piece is going to be minus u. So it's going to be minus t over square root of n. Minus, now we're going to have to do the square. So the square is going to become t squared over n, and we have a factor of 2. Right? What's the next term going to be? It's going to be minus t cubed over 3 n to the 3 halves. But we multiply by n. When you multiply by n, once you get to the t cubed, remember t is a fixed number. N is going to infinity. T is fixed. We're evaluating the moment generating function at a fixed t. N to the 3 halves is much, much larger than n. When I multiply by n, I'm going to still have a square root of n down below. That term is not going to matter in the limit, nor is the next, nor is the next, nor is the next. You can show that the tail is dominated by a geometric series. So you can show that the sum of all the other contributions doesn't matter. Let's look at the main term. We're going to have a minus square root of nt. Minus and a minus is a plus. N divided by square root of n is square root of n. So we get plus a square root of nt. Minus the minus t squared over 2 becomes a plus. The n's cancel. We get a t squared over 2. And then everything else, we're going to have, a t cubed over 3 n to the half plus a t to the 4th over 4n plus a t to the 5th over 5n to the 3 halves. You can show that that's bounded by a geometric series that's going to be at most 1 over some multiple of 1 over square root of n. Is everybody comfortable that this is enough detail? I can go into more detail. They don't let just anybody teach this class, right? You've got to be able to show that this is small. If you want, happy to show that it's small. People comfortable that you can bound this with a geometric series. So bound with geometric series. So just pull out a t squared, and then it's going to look like t over square root of n. Those extra 3, 4, 5 just make it converge a little bit faster even, so it's not a problem. Okay, square root of nt plus square root of nt is 0. So we get the log of the moment generating function of Zn of t is t squared over 2 plus something of size 1 over square root of n. Well, if that's the logarithm, how would I figure out what the moment generating function of Zn of t is? Yeah, I exponentiate. So we get the moment generating function of Zn of t is just e to the t squared over 2, e to the something of size 1 over square root of n. Ooh. So as n goes to infinity, this is going to e to the 0, and what does e to the 0 go to? 1. So the limit as n goes to infinity of the moment generating function of Zn of t is e to the t squared over 2, which is the moment generating function of the standard normal. And there is the proof for the special case. So everything worked out. And the reason everything worked out is because we had a nice closed form expression for the moment generating function. We could then plug it in and then just expand. Unfortunately, we're not always going to have a closed form expression for the moment generating function. Does that mean we're in? Yes.
Why is the log and e cancel out the second line?
The second line?
The second to third line, like this log e.
Oh, because I'm taking the log of e to the negative square root of nt. So the log of e to the a is a.
That's L and e to the.
Log is ln.
Oh,
So log equals ln in college. Once you leave high school, all logarithms are base e, except when they're not. When are they not? If you're working in computer science, what might the base be? It might be base 2. And in some advanced math, log sub 2 means log log. So in number theory, sometimes you actually have iterated logarithms. So you always have to be careful as to what notation is someone using. It's never a bad idea to ask somebody, what is your standardization? How have you defined things? So once we hit college, log is the natural log. And that's why the log of base e is going to work out beautifully here because we have an e to the negative square root of nt. You can see the e to the beta t that comes from rescaling is going to be very nice. Okay, we did it for exponential. I'm not going to go through and do the general case today. It makes no sense with on the order of 10 minutes left. I'll leave that for you to go home and maybe do the Poisson or the chi-squared. Do a distribution where you have a nice closed form expression for either the moment generating function or even better for the moment generating function of the sum. But sometimes if you do too nice of an example, you miss the general argument. There was a reason I didn't want to do the Poisson, I didn't want to do the chi-squared, because they're too nice. The moment I have a closed form expression for the sum of Poisson, it's Poisson. I have a closed form expression for the sum of chi-squared, it's a chi-squared. I wouldn't have to do some of the stuff over here, which is what I need for the general case. Exponential plus exponential is not exponential. So this was a much better example to do because it really highlights the general case. And so you want to ask, where do things change? Up to here, this would work in general. Nothing on this slide used the fact that we have an exponential random variable, except for one small part. Where did we use that we had an exponential random variable? So who can tell me where we used the exponential random variable? There are two places where it's kind of showing up. We take the mean, the average, and what do we subtract? I'm sorry? Lambda. That's the first place where we use the fact that we have an exponential. Where's the second place that we used an exponential? Divided by the variance down there. That was the second place we used. So instead of having a lambda in both of those places, one of them becomes a mu and one of them becomes a sigma. Not a big deal, right? So we would have to change that ever so slightly, and that's going to have some algebra propagations coming down. Okay. But this argument is going to be pretty much stable. That's not so bad. Now over here, this whole page, once we get to this part over here, now we're using the fact that we have a closed form expression for the moment generating function of the exponential. We don't have that in general, but we do have a series expansion. And so rather than having the moment generating function, we would have the series expansion, and we would have to look at a high power. And the hope is that only the first few moments are going to matter in the series expansion because we're evaluating it at t over square root of n. when you look at the higher powers, the mean, the first moment is going to have a t over square root of n. And we're going to raise it to the nth power. All right, square root of n to the n, that could be big. The next one is going to be a t squared over n to the nth power. Okay, those could still be comparable. But the next one is going to be a t cubed n to the 3/2 to the n. The n to the 3/2 is now bigger than n. That's not going to matter. That's where the universality is going to come from. All right, so given that we only have a few minutes left, let's prove log properties. It's not bad to review logs. Oops. Okay, so obviously I'm on the wrong thing, but it was, all right. So the first one is the log of x base b equals y means x is equal to b to the y. So that's what a logarithm means. So this is the definition. So we have the log base b of x1, x2 is the log base b of x1 plus the log base b of x2. And the proof is if the log base b of xk equals yk, that means xk is b to the yk. So if I look at x1 times x2, that's going to be b to the y1 times b to the y2. Well, what's b to the y1 times b to the y2? B to the y1 plus y2. And now by definition, if I take the log base b of both sides, I'm asking what exponent of b do I need to raise it to get x1 times x2? And given that I know x1 times x2 is b raised to the y1 plus y2, it's really not that hard to figure out this is just y1 plus y2. Okay, so this is the first one. The log of a product is the sum of the logs. Next one to prove is the log of x to the r base b is r log base b of x. And the proof again, if the log base b of x equals y, that means x is equal to b to the y. So what would x to the r be? That'd be b to the y to the r. But what is b to the y to the r? B to the yr. Or b to the ry. I want to write it as ry. It doesn't really matter. And now, if I take the log of both sides, the log base b of xr is going to be r times y, but y is just the log base b of x. And there's the proof. What's the next property to prove? Nope, change of basis last. You always hold off on that as long as possible. We've done logs of sums, we've done logs of powers. What's next? Division. So take r equals -1 to get inverses, and then use the power law and product to get quotient. I could prove the quotient directly, but the log base b of x1 over x2 is just the log base b of x1, x2 to the -1. And then that's now the log base b of x1 plus the log base b of x2 to the -1, which is the log base b of x1 minus the log base b of x2. So it's always nice to use earlier results to prove later results. Now, the last one is the one that in some sense is the most important for probability. Things have changed. When I was a kid, all books had to have tables of probabilities of normal distributions and other things. This is the 21st century. You're not going to do that anymore. It's all online. It's a pain to have tables for different distributions. So if you have a table for the normal distribution, if I give you something that's not the standard normal, I can just adjust and use that table by just changing so that I now have mean 0 and variance 1. So the last one is the change of variable. So the log base b of x is the log base c of x divided by the log base c of b, if I remember correctly. And the proof, well, let's see. The log base b of x equals y means x is equal to b to the y. Now I want to look at the log of x base c and the log of b base c. So what would be the log base c of x equals, say, w, means x is equal to c to the w. But what do we know about x? X is b to the y. And if we look at the log base c of b equals, say, u, that means b is equal to c to the u. So we want to figure out how should we express things. We know x is b to the y. I want to now look at writing things in terms of c. So how would you like to do the algebra? I've introduced some new letters w and u to help. Yeah, so we've got b is c to the u. So using this gives us x is equal to c to the u to the y. So if we take the log of both sides with respect to c, we would get the log of x base c is u times y. Y is just what we started with, the log of x base b. So this means the log of x base c is u times the log of x base b. But what is u? U is the log of b base c. So we have the log of x base c divided by u, which is the log of b base c, is the log base b of x. And that finishes the proof. So this is the change of base formula. This is probably the most forgotten. This is the one we have to be a little bit clever. Again, this is the time of the semester where you're starting to think, what do I want to take next? Do I want to take some of the more theoretical classes like real analysis, abstract algebra? Do I want to be a math major? In those classes, you're going to have to start doing proofs like this. One of the best strategies for proving things is just write down what you know. Write down what you're trying to get to. And then you have your start, you have your end, and you start to see, where can I go from the start? Where can I go from the end? Can I find some way to make something match up? And then, here's a path I can then take. Can I find some way like that? And so I just start off with this, okay, well, let me start off with everything I know. And I know I want to end up with things involving the log of x and b base c, so let me write those as well. How can I connect everything? And then the proof almost just flows off the page. All right, so this gave us a proof of the central limit theorem in the special case of exponential. Over the next few days, the homework assignment isn't that big this week. Try to do either the chi-squared or the Poisson, both directly by knowing that we know what the density is of the sum, as well as just mimicking this proof. And then that'll set us up beautifully for Tuesday to do the central limit theorem in general. And then we will start doing applications for the rest of the semester. All right, so this is a good place to stop. If you have